So apparently some people have been having a problem with how to approach assignment 8. So let's talk compatibility conditions. Because I think the issue is that the skill you need to cultivate is to be able to look at a situation that you might not have encountered before and be able to figure out what its compatibility conditions are. Because I can't list for you examples of all the possible compatibility conditions you're going to encounter. There's infinite number of different setups for indeterminate problems that would have different compatibility conditions. So I can what we can do is we can talk about how we kind of convert from what we know about the problem into equations that allow us to describe that problem mathematically, which we can then use to solve for the unknown variables. So let's, for example, we've got this one here. Got this, zoom in a bit more. Got this hinge. Sorry, we got this beam here that's kind of built out of 3 separate structures that each, and it's got these 2 hinges in the middle. So honestly, this isn't really an indeterminate problem, although it might look at one at first glance. Since we have those hinges there, we can, if we break this up, looking at this section here, BCD, just draw a free body diagram of that. We've got that weight there, and then we're going to have a reaction. So the hinge there at B, it's going to be pushing up on this thing, and the hinge at D is going to be pushing up on this thing. And I think it's safe to say that you guys are at a point now where you can figure out that for this thing to be in equilibrium, these 2 forces need to be equal. So the magnitude of those forces would just be that W times this distance here, so 0.8 meters divided by 2, because we're splitting it up into 2. So that's what's going on just in that thing. And then essentially at A, we've got again, the force from B, the hinge B. Hinge B is going to be pushing down on the cantilever AB, and then we've still got that distributed force here as well. So we got, I'll draw the concentrated one in red. So then we've got just transforming this into a free body diagram. And then we'll have a reaction at A, AY, reaction in X, so that's 0, and then we're going to have a moment. And then we can solve for that. So our AY, sum our forces in the y direction, and we'd end up with AY is equal to this, this plus this. So that'd be if the W, this here is W naught times 0.8 meters divided by 2. So W naught times 0.4 meters. And then this here, this is another 0.4 meters. So AY would just be equal to W naught times 4 meters. Oh, sorry, 0.4 meters. Which is exactly what we expect, because if we take the entire W naught, multiply it out over the 0.8 meters. adds up the 2 0.4s, and we get to 0.8. Take that W naught, multiply it out by the 0.16 meters, and it's still symmetrical, so evenly distributed. We still don't know, but we wouldn't have been able to tell at a glance what our MA is. So our MA, again, we just need to go from there, and we need to figure out yeah, some of the moments at A is equal to 0. So it's going to be MA minus the moment from that and the moment from that. We can solve for that. So we're able to solve for the moment reaction based upon that we wouldn't have otherwise been able to just from a glance. So here, something like this, our compatibility conditions are going to need to be that the displacement at A is equal to 0. The displacement at B is also going to be equal to 0. And then the slope at A is equal to 0. And the slope at B is equal to 0. And those will be the conditions that you need to have for basically any beam that's set between two walls. If you've got a rigid connection on either end, that's what you're going to need to do. So, for example, if we go to our beam bending formula, which, come on, the PDF needs to open up. So if we go to our beam bending formula, then the ones that we could use for that, essentially what we're going to need to do in order to kind of get a loading condition that meets this, we've got our W naught, sorry, our W here. So we're going to need to use the formula that corresponds to that one. So we use that. And then in addition to what's going on with that cantilever beam, we're also going to have to basically apply at B a force and a moment. So we're going to need to push it up enough that it gets into place, but we're also going to need to twist it enough that it stays straight. So that would end up being this one here. And this one here. Okay, so so we've got a couple other things that we know about this situation that we might be able to apply as well. They wouldn't necessarily be applicable for all beams stuck between two walls thing, but we also know that if we just look at this, we know it is symmetrical, so therefore we can tell that a y and by. Here, I'll draw the moments here. As well, our AY and our BY, they need to be equal as well. So we can figure what the magnitude of this BY here is. So that BY is just going to be the W times L over 2. So that would be the magnitude of that force there. Pushing upwards, obviously. Again, when you're using the beam formulas, you need to keep in mind the directionality. So all of these formulas are formulated such that a downward displacement is positive, and the loading situation needs to match kind of what's in the graph. So if you've got a force pushing upwards on the end of the beam, then that's opposite of what's on the graph. So we should expect upwards displacement, so that'd be negative, given if we're using the negative for these formulas, and then just everything adds up. So similar idea for this, same idea. What we're left with here is we are left with, right, let's just draw a quick free body diagram of this. We got an m naught, and then we're going to have a reaction force at B. I'm going to assume it's going like this. It's downwards, By, and we're going to have a reaction force at A. But that can't be all, because again, our compatibility conditions still need to be met. Our compatibility conditions are for this, that our displacement at A is equal to the displacement at B, which is equal to 0. And then the slope at A is equal to the slope at B, which is equal to 0. So we're also basically gonna end up having some moments applied at A and at B that are gonna keep this thing straight as well. So like if we crank on this thing, like if these things were just pinned, and we cranked a moment like that, then essentially what we expect is we'd expect to get displacement like this. Here. This is an exaggeration, but it'd do something like this. But it can't do that because of this compatibility condition. So in essence, what we're going to need to do is we're going to need to apply additional moments that counteract that tendency to rotate there. So we're going to have an MB there, and we're going to have an MA there that counteracts that. So if we want to look at this, essentially, we know that AX and BX needs to be equal to one another because they're the only vertical forces. So AX and BX need to be equal to one another. And therefore, as a result, AX and BX need to be equal to one another. Then we can also expect that MA and MB need to be equal to one another too, because in this situation, it's symmetrical. It's not symmetrical about this axis, it's symmetrical about that plane. So our MA and our MB need to be equal to one another too. I think the easiest way to deal with this would be to essentially use the pinned connections as our baseline, and then apply rotations to the end that force things back. So for example, let's see, where we got that. So yeah, in the formula sheets, we've got simple support to the moment load. So this ends up giving our, the key conditions that we're worried about are the slopes at the two ends. So the slope that would be caused just by that moment in the middle can be found with this formula here. And then essentially we just need to go back and apply a moment on either end. Apply a moment on either end. Again, those moments need to be in equal and opposite directions. And applied it the other end, and then basically we just need to take the combined effect of the slope at either end due to here we'll just draw this out here. So the slope at A and B due to, oh wait, that one didn't. I did that backwards, didn't I? Due to the moment in the middle, the m naught, or the m naught, due to the moment applied. How did I mix up A and B too? A, B, there we go. Due to the moment applied at B, so we apply a, well, let's see, if we're trying to counteract this rotation, then that is going to cause it. So if this thing is sloping like this, due to the applied moment, then the rotation applied at the moment applied at B to counteract that would be this way. So we're going to get something like this. Let's see here. We're going to get something like this at A, and then similarly, from B to A, and then for the moment applied at A. Oh wait, no. It's gonna, we're trying to counteract this rotation here, so it's going to try to do something like this. So it's going to cause something like that. Maybe more so like that. So essentially just add up that slope there, that slope there, that slope there, equal to 0, and then that slope there, that slope there, that slope there, equal to 0. Something like this one. So again, we have the only real compatibility condition that it matters here is the displacement at C max is equal to 0. So no, max is equal to delta naught. So it could be less than that amount, but if this load here applied to that beam would cause that thing to drop down less than more than that amount, then it's going to hit resistance, and it's going to hit enough resistance to limit the displacement to that amount. So again, going back to our formula sheet, that would be basically this formula and this formula. We get to use S1 instead of using S2 because it's in the center. And in both those cases, that the point we're worried about is in the center, so we get to use the delta max formula instead of the generalized one. We could use the generalized one. It just happens to work out to the same thing at the L divided by 2, at x equals L divided by 2. Obviously, still check that that your beam would hit that before you start doing that, because otherwise what you're going to do is you're going to end up with a calculation stating that the reaction at C is negative something or other, and that just can't be the case because it doesn't come into contact with that thing at that point. It's not pulling it down. It can only push up. For something like this one, so we've got this cable here. Got this cable here. Got a cross section. We're told what sort of material it is. It is at the end of this beam. So our compatibility condition needs to be that that essentially we are going to get a force arising in that cable when the cable stretches. Cable works the same way as a spring. You can just treat that as a big spring. It can be a cable, it could be a rod, it could be it could be a big spring or whatever. When you stretch it, that's how you get tension. So if there's no displacement, like if we get rid of the load, then there's no there's not going to be any displacement downward at B, so there won't be any force arising in the rod or in the cable or what have you. It's only once we start pushing down, pushing B down, that we get that stretching that causes that force. So we're going to basically end up, we're going to end up, if we do a free body diagram of this thing, we're going to end up with, we got a CY, got the distributed loads. Oh wait, no. And we got our BY that is caused by the stretching of that. And then we're going to have some sort of moment at C. So what we need to know here is that the magnitude. So again, so if we got this, we're given the cross section here, or the we're given the cross section, so we know that the displacement of a rod that is stretched is going to be equal to the force times the length over EA. So I'm assuming we're told the material, so we know what E is. We're given A, we know what that is. We're given the length. So we know essentially that the displacement at B is equal to BY times L over EA. So that we need to use that BY in the formulas. So that is our compatibility condition. So when we go to look at our cantilever beam formulas, we'll use this one. We'll use that one. And we'll use this one. And then essentially, the total displacement at B is going to be equal to the displacement at B for this plus the displacement at B for this. And again, keeping in mind they're acting in opposite directions. So let's call this. So we're going to have a displacement BC3 plus displacement BC1 is equal to the displacement at B. And so again, if we keep the sign convention from the formulas, this one's going to be negative because it's pushing, because that force there is pushing up and not, pulling up, not pushing down. And then that B here goes into here and goes into the formula for BY, which goes in to that formula there for the displacement at B. So you're going to end up solving for something that looks like, it'll be like, there'll be a BY term here, and by L to the 3 divided by 3EI, and then this term here will have by times L over EA, again, different L. We're using this L, not that L, for this one, over EA. So then, again, we got a by term here, we got a by term there. We can solve for that because we know everything that's in this, we know all the stuff that goes into our delta B C1 term right here. For something like this, if we just do a free body diagram of the thing ABC there, we got 30 kilonewtons per meter pushing down. I should have drawn that there. Let's 30 kilonewtons per meter. I need kilonewtons per meter. So the resultant of that 30 kilonewtons per meter times 4.4 meters, what is that? 132. 132 kilonewtons. And then we have a reaction at A and a reaction at C. And we're also going to have a reaction at A in the X direction, but that's 0. So we don't need to worry about that. So I got a CY, got AY, and again, by now, that's symmetrical, so we know that AY needs to be 132 divided by 2, 66. 66 kilonewtons, and then same here, 66 kilonewtons. Then, on this DE here, all that's going on here is we've got a 66 kilonewton force pushing downwards in the middle there. So, simple enough there. We can just figure out what the displacement is with our C2 case here. For something like this, same idea really, but sorry, similar idea to the one we had before. So essentially, so similar idea to the spring ones. So essentially, if we do a free body diagram of our BCD here, so again we got B, we got a BY, we got a D, DY, and then when this cantilever beam here starts to push down, it's going to push down. So we're going to call that CY. And then if we just do a free body diagram of BC, CY is pushing up on that beam. And we're going to get an AY as well. And we're going to get some sort of moment. Moment at A. And then, of course, our distributed load. £50 per inch, like that. So again, the magnitude of CY needs to be such that the displacement, magnitude of CY is going to be based upon the displacement at C. So again, we got this pinned beam here. So we know that we can use these formulas here to describe the relationship between its displacement and the load. So we can get that's the displacement in terms of the load. We can reformulate that to give us the uh, load in terms of the displacement. And then we go back to the cantilever beam. I'm going to scroll up for that one. So cantilever beam, we've got the displacement of the cantilever beam at the end based upon just that force pushing up, and again, negative, and the distributed load. So basically, that's exactly the same idea as what we saw up here. It's just that the thing that's acting as a spring, where the force is proportional to the total displacement at the end of the cantilever beam, it's not a spring, it's not a rod, it's this other beam. But same principle applies. Formulas are going to end up very similar. So let's see here. This next one here, very similar to the one in the assignment, and again, kind of looking up at what we saw for the first one I talked about. It's at a first glance it might look like it is indeterminate, but it's really not. Because if we just take a free body diagram of ABC, we're going to have some force Cy at the hinge. We're going to have a force AY, a force Cx at the hinge that equals 0, and then we've got this 800-pound force right there. We've got two unknowns, and we can use our sum of the forces in the y direction and our sum of the moment equations in order to solve for that. So we can figure out what Cy is there, and then from that, on this cantilever beam CD, that is just going to look like that. Simple enough. That so based upon our cantilever beam, we can figure out what the displacement is there. Figure out what the displacement is, and we can figure out what the moment is as well. So something like this, compatibility conditions. The compatibility conditions that exist, displacement. No, that looks more like a sigma to me. Close enough. Displacement A is equal to 0, and that's also equal to the displacement at B. And then just the slope at B is equal to 0. So I think the easiest one to do this would just be to use the cantilever beam formulas and use this one where our P is the reaction at A, and then use this one where the P is the actual P applied. Something like this, we get a spring in the middle. So again, that relates to the displacement. So if we have a spring in the middle, then we know that the displacement, the force of the spring, we'll call that By, that needs to be equal to K times the displacement at B. Now again, that displacement at B is not due just to this W. That displacement at B needs to be the sum total of the displacement due to the distributed load so S3 come on, paste displacement due to that S3 BS3 plus the displacement due to the point load pushing up. BS1. So the fact that we're pushing down increases the displacement and thus would increase the force in the spring more, but the spring pushes back up. So as it does so, it decreases the amount of displacement that occurs and thus decreases the amount of force generated in the spring. So you got to take both those things into account. Something like this. Again, kind of the same idea. We've got this force here. You've got these two cantilever beams. The force is applied in the cantilever beam. So if we have a look at AB, that it just has a force coming down. Call that CY, so that's the contact points at C. And then we got AY and BY. And then for DE here, we've got, we're going to have a DY, EY. Then we've got that CY pushing up. And we've got this 2 kips, this is 6 kips pushing down. And then again, we just need to kind of go to our formulas because we know that the magnitude of that CY is going to be determined based upon the displacement of that beam. How much that beam goes down is going to determine how much that displacement is. And similarly, when we get to this one, how much the magnitude of that is going to determine how much that beam would be pushed up to counteract the 6 kips. So it's the relative stiffness of the two. The relative stiffness of the two beams is in part going to be what determines kind of how much of that 6 kips makes its way through CDE to get to AB. Or ACB, I guess. So, but again, we'd be kind of using the same similar formulas to here. What happened? OneNote was being funny with me. Okay, so got something like this. Now, for an overhang, as long as we're not worried about what the slope is right here, which we're not, because our compatibility conditions are going to be the displacement at A needs to be equal to the displacement at B needs to be equal to the displacement at C, which is equal to 0. Then we can essentially replace these forces here with an equivalent force moment couple. And if we did that, then essentially that's going to cause between A and C, that's going to cause the same displacement shape as if we as P will. Just that moment will do it, because the force itself applied at A, if you're pushing straight on the hinge straight on the pin just pushes back. But at that moment, there is what's going to kind of cause your displacement in the middle. So like we're gonna get if we only just applied a moment in the a moment here and a moment here, we're gonna get something like this. Whereas on the other end, we're we still got continues on, but our formulas are based kind of on what's in the middle there, so we can work with that. So essentially, what we can do is just replace that with a setup where we've got P, B, the moment is equal to P times B, so B and P. And then since that would otherwise cause an increase in the that would otherwise cause it to move upwards, we're also going to have a negative y direction reaction at B. So I'll call that By. So looking at our tables, got our S1 here, so we'll use the S1. Come on, use the S1, and then we just need to use this S6. And we need to use this 6 based upon what happens in the center. And since kind of P, the moments being applied are equal on either side in this case, essentially we can kind of just say that our displacement at B, which is equal to 0, needs to be equal to 2 times that, so 2 m naught L squared over 16 EI. Oh, although based upon the formula here, keeping in mind that that m naught there was based upon a rotation at that end. We're rotating the other way, so that's negative. And then when we get to this load here, that's going to be positive, so plus PL cubed over 48 EI. So from there we can solve, so we know what our m naught is. Our m naught is the P times the B. In this formula here, our P, that's the By. And then we got our L, we got our EI, so on and so forth. So we're able to solve for what that reaction is, and then we can draw draw our diagrams as needed. Similar idea here. We could kind of treat it as an overhang, but I think probably the simplest way to do this would actually just be to treat it as if it was a moment and a point force, because we're going to have our compatibility condition be that displacement at B needs to be equal to 0. So keeping in mind that that location B, that's not really anywhere special for any of this. So when we go to our cases here, we're going to have to be using this generalized formula here, which for some of them can be more complicated than the formula that's already solved for in the middle. But we'd have that one, and we'd have this one, if you're worried about kind of which one to use here, since the point that we're looking at is the point of application of the force, x equals a, either of these formulas works. We've got this one here. Again, our compatibility conditions are going to be based upon the contact point here. So essentially, we're going to have, for AB, it's going to be pushed down. It's going to have a certain amount of displacement B, and the magnitude of that force By is going to be proportional to that displacement. And then for AY, got the distributed load, and then we got BY. So again, our BY there is still proportional to that displacement B, where our displacement B needs to be equal to the sum of the displacement caused by the distributed load plus the displacement caused by BY pushing back up. Also, the concept of compatibility conditions comes up in non-beam stuff. So for something like, say, this, we're applying some sort of torque. Applying some sort of torque in the middle, and that is going to cause, if we do a free body diagram of this thing, we got a torque here, it's going to cause some sort of reaction there, some sort of reaction there. We're going to get a certain amount of twisting in this section and in this section based upon their internal torque loads. So we know that just based upon our sum of the moment about the x-axis, that the MA plus MC is going to be equal to T. And then essentially we're going to get, so like the internal load in this bronze section here, based upon the directionality that we've got here, that'll be a positive MA. And then it drops down by T. And then for the steel, it's a negative MC. So MA, negative MC. And we know that they're originally mounted, so the total twist between A and C needs to be equal to 0. And that's just equal to the total twist between A and B plus the twist between B and C. Now, obviously, they're going to be different signs, different directions, because the torques in opposite directions during those sections as well. And you just got to pull out your formulas for the twist over section, plug it in. Similar idea here. Got the set of gears mounted to shafts, and the shafts are, for whatever reason, mounted to the wall. So if we apply this torque here, that is going to cause a certain amount of twist in AB. And then if this thing rotates, those gears mesh together, and it's going to cause a certain amount of twist in CD as well. And based upon the Let's see here. Based upon the gear ratios that we've got, we know that the twist in CD needs to be more than the twist in BC. Sorry, AB. Because for this thing to turn, basically for if this thing has two-thirds of the radius of the top one, then essentially that means is that for every full turn of this gear, there needs the number of the teeth that are meeting in here. They're happening linearly based upon the distance around the circumference. So for every full turn of this one, we need to have 1.5 turns of this one. So our twist in CD needs to be equal to 3/2 twist AB. So that's our primary compatibility condition. The other one that we know is kind of when we just do a free body diagram of A, B, and CD. So we're going to have some sort of reaction at A. We've got this torque that's applied, and then at where the teeth mesh, we're also going to get basically kind of a contact force. So those two things, those teeth are going to push against one another. So we're going to get a reaction there as well. So that's going to cause a force that causes a counteracting torque. That being said, it counteracts, so it's going to be pushing this way. So we'll call that FBD is the force. Therefore, the torque that it would use to counteract is going to be FBD times R. And then at C, we get a similar idea. Just draw a free body diagram of that. It doesn't have any external torque applied, so the only torque that gets applied is just based upon that contact force. So that, again, it's happening equal and opposite direction. So for this one, it's pushing this way. So the torque that's going to be generated, that's just going to be FBD times 2/3R. So if that's FBD times 2/3R, then that means that if we take then that means that the reaction at the reaction at the wall, MC, needs to be the same amount as well, just opposite directions. So our twist over CD is going to be based upon the internal torque that's here, and then we can relate it back to AB from here. So we'll have two unknowns here. We don't know what we don't know. We know that the we can relate what MA is and MC is in relation to the torque applied as a function of BD. So between the two of those, we've got we've got two unknowns that relate to one another. So MA and MC could be found in relation to one another through FBD. So we need to know what FBD is and one of these reactions, and we can use that to find the other one. So from that, essentially two unknowns, and we got the two twist equations. So from there, plug those values in, and we can solve for what those are. Something like this, axial. So if we've got some sort of rigid, like, I don't know, tabletop or something, and then we got these 3 bars that are supporting it. If we are going to be applying some sort of force up or down or what have you, then this thing is going to have a certain amount of displacement. And then since these things are kind of all mounted together, that means that the displacement in these needs to be the same. So our compatibility condition, copper is equal to steel. And so that's our compatibility condition for the force, and then, for the displacement, and then our compatibility condition for the force that's applied. So let's say it's pushing downwards. If it's applying force downwards, then these would cause a compressive force. But the magnitudes of that is just going to be, let's call this P. So the magnitude of that, P is going to be equal to F steel plus 2 F copper, because there's 2 of those copper things. So 2 unknowns and 2 equations that we can use to solve for that. Similarly, here we've got a similar setup, but there's a gap here. So our compatibility conditions are that the displacement in the steel needs to be equal to the displacement in the aluminum minus that gap that gets closed. Oh wait, no, sorry, plus that gap that gets closed. So the steel needs to compress 0.1 millimeters more than the aluminum does. And then for the force, it's 400 kilonewtons here. That's going to be equal to the F in the aluminum plus 2 times F steel, because we got 2 of the steel ones. Simple enough. We can solve from there. Something like this. So we got this weight here being attached. So hey, let's just replace that with, that's a force, 50 kips. And I really hope that I've drilled it through everyone's head that a pound mass in Earth's gravitational field weighs 1 pound force. So if this is a 50 kip mass hanging from this beam, it is going to weigh 50 kips force, assuming we're not on Mars. They probably would have mentioned it in the problem if we were on Mars. So yeah, 50 kips. And here we're told that this beam here is rigid, and then it's supported by 2 rods. And those rods are not rigid, so they are going to flex. Essentially, we can relate how much they're going to flex just based upon the geometry. So if if this thing rotates to some small angle here, then the amount of displacement in the steel, how much the steel is going to need to stretch in order to accommodate that, and the displacement in the bronze, those are just based upon similar triangles. So the displacement in the steel is going to, let's see, we got a total of 12 feet to the steel, and we got a total of 3 feet to the bronze. Therefore, the steels, in order for this thing in order for this beam to stay rigid, to stay straight, it needs the steel needs to stretch 4 times as much as the bronze does. So we got that. So therefore we can. Oh, I forgot to put the 4. So 4 times as much displacement in the steel as in the bronze. That means we can also relate the forces to one another. So again, just keeping in mind that our displacement is equal to FL over AE. So plug in the values from here for the bronze, and then do the same thing for the steel, and then we'd be able to solve for what those two forces are relative to one another. So we get something like, I'm just going to make up values here. So let's say that's going to be like F steel, and maybe, oh wait, no, it's pulling up. There we go, F steel. It's pulling up, but the displacement's 4 times as much in the steel as in the bronze, and yeah, the displacement's 4 times as much. Let's see, the area is bigger for the bronze, but the steel's stiffer. So let's say that this ends up being 0.25 F steel. And then we're also gonna get an OY. Used O for origin for the location there. Actually, that looks. I'm relabeling that A because O looks too much like a 0. And then we got the 50 kips here. So from there, we can just, we can take the sum of our moments, take a moment through A, and then we're able to solve for what our F steel is. So I'm going to go ahead and do this problem to kind of hammer home the example here. So got an overhanging beam with 3 supports. Determine all the support reactions. So like I had said earlier, the easiest way to model this, because the only points where we're worried about displacements are at A, B, and C, we can model that by essentially going P and then P times B, and then P, and then P times B as our moments, and then we'll have an A Y, and we'll have a B Y, And we know that that by is going to be pulling down, because otherwise this thing's going to have a tendency to want to flip up in the middle. And then we'll have a cy. So this and this aren't themselves going to cause any displacement in the beam. Putting a load directly over the support doesn't do anything but just increase the magnitude of that support. So what is going to cause displacement are these two PB1s. So we can treat that as if we've got this is the situation going on. So going to our beam bending formula, let's see here. So we're going to want S1. Let's put that right there. And we are going to want S6. Yeah, let's stick that over there. So, essentially, the condition that's going to prevail here is just our displacement at B needs to be 0. So our displacement at B needs to be equal to 0. So 0 is equal to, again, I'm going to be keeping with the convention that downward is positive. So we'll start with the S1 case. By times, let's see, our L3. So given the geometry that we're told here, our L is 2a, 2 small a. So 2a cubed over 48 EI. And then PB here, so again, it is the opposite, it's pulling in the opposite direction as this one shown here. So that's going to cause a negative displacement. Minus, so the M naught is just P times B times L squared, so 2A squared divided by 16 EI. So that's what's happening based upon that one. And then we got an equal one on the other side that would cause a completely equal displacement in the center. So I'm throwing a 2 there. I'm moving that minus sign more away from underneath the 2. Or actually here, let's cancel out that 2 and we'll make that an 8. There we go. All right, so to simplify things up a little bit, let's multiply everything by EI. So that goes away to the other side. Now let's multiply everything by 8. Cancel that out. That turns into a 6. So that gives us by times, let's see, 2 to the third, that's 8a cubed divided by 6 minus p times b times, let's see, the 2a squared, that's 4a squared, nothing on the other side. That's equal to 0. All right, so moving that over to the other side, we got by. Let's just solve for what by is. So pb times 4a squared, then divide by this, divide by 8a cubed times 6. So cancel out the 4 to get a 2. A 2. Cancel out the 2 to turn that into a 3. by is going to be equal to 3. Oh, cancel out the a squared here. That's going to be 3pb over a. So yeah, 3pb over a. So from there, we can use that. Now we can solve for what our other reactions are. So if we just had okay, we got p. We'll go back to the full one. We got p there and there. We've got ay, got cy, and we've got 3pb over a there. So this is a from here to here, and a from here to here, and then b from here to here. So if we just take a moment about a, that's 0. So let's see, we got this p here. So that'll be a counterclockwise moment. So that'll be p times b. Now let's do the other p while we're at it. That'll be a clockwise moment. So it'll be minus p times b plus 2a. And then we have the force at b. That is also a clockwise moment, so it's negative minus 3pb over a times that a distance here, so that those a's cancel out. And then we got cy. Cy, that'll be positive, so cy times 2a. 2a is the span from there to there. So, okay, solving for cy. Let's see, 3pb minus 2ap minus bp plus, oh wait, no, sorry. (3bp) gets added over to their side because it's negative on this side, and then these terms also get added over because the negative sign there. So plus pb plus 2ap, and then minus this term here, minus pb is equal to cy times 2a. All right, so how many PBs do we have here? So that one cancels out that one. So just 3 PB and plus 2AP. Or we'll just put that P times 3b plus 2a is equal to cy times 2a. Now we can divide that out. Cy is equal to p over 2a 3b plus 2a. Or let's see here. Cy is equal to p times 3 over 2 b over a plus 1. And then we can, and then just looking at this, that's symmetrical, so therefore ay needs to be equal to cy as well. So yeah, there's another example. So just you need to get in the frame set of figuring out your compatibility conditions by looking at how does this thing deform based upon the supports and the loads, and how do I describe that in equations. Not all of them are going to be that you encounter are going to be familiar. They're not going to be a carbon copy of something you saw in the exercises. And the goal here is to be able to figure out what those equations are, not just use ones that you recognize. Yeah, cheers.